Hello, everybody. All right, welcome to lecture 12. This is an exciting one because this is going to be the first time we are now going to start talking about non-parametric tests. And as I was reviewing and preparing for this class, I realized that, I think you all are going to really appreciate non-parametric tests, right? It's a lot more straightforward than the parametric counterparts. And I had alluded to a kind of a little cheat sheet or a cheat table, and we're going to go over that today in this slide. So, without further ado, let's begin. I just want to go ahead and point out that there's a couple of files that we're going to be working with today, right? So we have the FNES 702 lecture 12 slides. We have a SAS program. We call it the manu.sas. We have the manu dataset. We have the Wilcoxon SAS or code, and then we have the Wilcoxon dataset, right? So that should give you a hint today that we are going to go over 2 non-parametric tests today. Okay, so without further ado, let's begin. So today the objective is we're going to go over what is a non-parametric test. We're going to go over the types of non-parametric tests that we are going to expect you to know. And then actually 2 of those non-parametric tests that we're going to cover today are the Mann-Whitney-U and the Wilcoxon signed ranks test, right? I always, when I took stats early on, the names always kind of like helped me up. It was always just like, especially in the non-parametric tests where the names all start getting a little weird. But don't get hung up on it too much. I think that once we go through this lecture, it'll make a lot of sense. All right, so here we are, non-parametric test. A non-parametric, so this is really the big difference right here, right? A non-parametric test does not assume anything about the underlying distribution or anything about the data, right? For example, that the data comes from a normal distribution, right? So let's think about this for a second. We've been talking about parametric tests. We've been beating, parametric tests and the assumptions to death, right? Essentially, when we first went with it, we just made the assumption that like, hey, parametric test has these assumptions and we're going to assume that none of them have been violated. After that, we made the shift and we said, well, actually, okay, we can't assume anymore, right? Like, let's actually test these assumptions, which you all know how to do now. But then the question becomes, well, what happens when the assumption is violated, right? And the simple answer is, well, if the assumption is violated, then just use the non-parametric counterpart, right? What do I mean by that? You'll see in about 2 slides when I show you the grid, but ultimately, if any of the assumptions are violated, you then go ahead and there is an equivalent test that you can go ahead and run, right? So when the word non-parametric is used in statistics, it usually means that the population data does not have a normal distribution, right? Remember the normal distribution, you have your bell curve, right, or the quotient distribution. You have your, excellent folks or your high achievers all the way to the right, and then you have your lower achievers to the left, and the vast majority of the folks kind of fall within the middle, right, a normal distribution. So let's go over some features of a non-parametric test. Typically, the data is nominal or ordinal data, and if that rings a bell but you're kind of like, hey, I don't really remember what that is, go back to, I think it's lecture 2 and review. The data does not need to be normally distributed. If you have outliers in the data, right, that's okay, right? Remember and I think, as we go over this, I'm going to use the bar example where everybody's in a bar and then Jeff Bezos walks into the room. He's an outlier. He drags everybody's mean salary up. so we don't want to use the mean anymore. We want to use the median because of Jeff Bezos, right? But in this case, and then in a parametric test, we wouldn't be able to use a parametric test if Jeff Bezos was in our data set, right? So what we'd have to do is we'd either have to get rid of Jeff Bezos out of our data set or use a non-parametric test, right? We had talked about variances having to be equal for a parametric test, and we test for that, right? And, we take the larger variance divided by the smaller variance, and if it's less than 4, then we're good. But what happens if it's greater than 4, right? Well, if it's greater than 4, then you have unequal variances, and you can't use a parametric test, right? So that, boom, pushes us over to a non-parametric test. And then the last thing, and this is one item that we really haven't talked about, is just sample sizes, right? But if the sample sizes get too small, non-parametric tests are okay. They're okay with dealing with small sample sizes, so just kind of keep that in your mind. Other reasons to run a non-parametric test: one or more of the parametric test assumptions have been violated, right? So we're kind of just rehashing here. One of the assumptions have been violated, boom, come on over a non-parametric test. Your sample size is too small, boom, run a non-parametric test, right? Your data has outliers that can't be removed, head on over, non-parametric test. And then the key one, and then this is kind of if you remember the Jeff Bezos, right? And I'll give you the scenario again. We have a bar and it's filled with police officers, right? You know what, let's not do police officers. We always do police officers. Let's say the room, we go to a bar and it's filled with teachers, right? How much do teachers make a year? What, 200,000? Just kidding, right? So I know teachers are making somewhere in the ballpark of, say, $80,000 to $100,000 a year, right? And this bar is frequented by teachers because it's right next to a high school and it's Friday night, so everybody's going out for happy hour, and everybody's a teacher, and everybody makes between $80,000 to $120,000 a year. And then Jeff Bezos walks in, right? And if Jeff Bezos walks in, and now he's I don't know, is he a trillionaire? He must be a billionaire at least, right? Now, he skews the distribution, and now every teacher is a multimillionaire now, right? The average salary of the individuals inside the bar now are in the millions by proxy that Jeff Bezos is so rich. And so we can't use the mean anymore because you're not telling a story, right? Imagine there's a New York Post headline now, average a mean salary of teachers in this bar over $1 million, government misuse of spending, right? Some sort of, you see how there's no truth in statistics, right? That's what we said very early on. But in reality, you shouldn't use mean, you should use median, right? And if you want to use median, I guess that was a long-winded way of saying, if you want to use median, then you would use a non-parametric test. Now, excuse me, this is going to be a very, very handy sheet for you. Just moving on into the future, right? We have in the very, very first column here our parametric tests. You know about these now, right? You know when to use an independent sample t-test. You know when to use a paired t-test. You know when to use the one-way ANOVA, right? And we're going to jump over to this last column right over here. When you have two different groups and you want to go ahead and compare, right, then you would use an independent t-test, right? When you have one group that's tested twice, you'd want to use a paired t-test, right? The pre-post, you'd want to use a paired t-test. And then when you have more than two groups, you want to use the ANOVA. Now, let's say, hypothetically speaking here, one of the assumptions were violated. It's not normally distributed. You have an outlier. Except your variances are not equal, right? Then you go ahead and you just simply go over into the middle and you pick the non-parametric counterpart. So let's say we have a pre-post scenario that we're thinking about. Oh no, assumption was violated. We would do the Wilcoxon signed rank test. If you had a scenario where you decided that you're going to do the independent sample t-test, you would do the Mann-Whitney test, right? It's actually Mann-Whitney U test. Good. And so today we are going to cover these two right here, the Mann-Whitney U test and the Wilcoxon signed rank test. And then our next lecture, we will cover the Kruskal-Wallis test for more than two groups. Okay? So I just wanted to go ahead and just show you. This is what it looks like when you have data, non-parametric data, right? That's not normally distributed right over here. Okay? And now remember, visual inspection isn't always the case, so you have to be able to go ahead and run through your test to go ahead and figure out whether or not it's actually normally distributed. But sometimes you could just look at it and it'll tell you. But this clearly, just looking at it, tells you this is not parametric, right? There is no normal distribution here. For the most part, everybody has a 1, and then 2 people have a 2. Great. Okay, so Mann-Whitney U test. Mann-Whitney U test is to compare the differences between two samples when the sample distributions are not normally distributed and the sample sizes are small, less than 30. It is considered to be the non-parametric equivalent to the two-sample t-test. Okay? Really, again, I just can't emphasize this enough. You have to go ahead and figure out which test I would go ahead and use. Do I have two different groups? If I have two different groups, you know you're on this column right over here. Then the next step is to figure out whether or not it is parametric or not parametric, right? And if it's not parametric, you go Mann-Whitney U, which brings us back to here. Okay, so let's go through our case scenario. Suppose researchers want to know if ingesting caffeine leads to a change in the number of push-ups completed, right? So the thought process is this. Caffeine is an ergogenic aid. When I ingest caffeine, I'm sharper, possibly, maybe I'm stronger. So I want to go ahead and see if by giving a group of people caffeine before they do the max number of push-ups that they can complete, if it'll have an effect or not, right? Will it lead to a difference? So, to test this, they conducted an experiment where they measured two groups of participants. One group had caffeine and the other did not have caffeine. They were asked to complete as many push-ups as possible. So use the following data sets. Using the following files, complete the exercises below, right? So we are going to use the manu.xlsx and the manu.sas files. We want to know what is the null and alternative hypothesis, what is the p-value, interpret it, and is there a difference between the number of push-ups completed between the caffeine group versus the non-caffeinated group. Okay? All right, so we're going to fire up SAS, all right? And you are going to, by this point, you are an expert on this now, right? But we're going to upload the data set, and then we're going to upload the SAS file. We're going to use our proc import statement, right? We always use our proc import statement. And we're going to name the file that we're going to import work.manu, the data path. We're going to change the Excel file, and we're going to change the sheet name. We're going to go ahead, highlight that, and give it a running man. And now let's take a quick glance at our data set. The data set name, the columns. Seems like there are two columns here. One column name is group, and the other one is named num push-ups. And we have a drug group, and we have a placebo group right over here, right? So the drug group is our caffeine, and then the placebo group is our no caffeine group, okay? So now we're going to simply go ahead and preform the code that's going to give us the results for the man Whitney U, right? So we have, let's just take a look at this code. We have the data. Data is going to be man U. Notice afterwards we're asking for Wilcoxon, right? Our class, we're going to put group, right? When we go here, group, it's either the drug group or the placebo group. And then we have var, our variable, which is number of push-ups, right? Num push-ups right here. I'm going to highlight that. We go running man. And notice, here we are. We have our outputs right over here. We have the sum of all of the scores in the 2, right? So if they went ahead and summed all of the scores, they could be here. We have the mean scores, and then you'll go ahead and notice our p-value, which is in this area right here. Notice Wilcoxon 2-sample test. Okay, we also have a figure, but let's go back to the slides and we will go over each and every one of these, right? Okay, so what is our null and alternative hypothesis? What is the p-value? And then is there a difference between the groups? Okay, so recall that the man Whitney U uses the following hypothesis. The 2 populations have the same median. That's our null. And our alternative is that they have different medians. Since the p-value, and I have to fix this right here, since the p-value is 0.2240, since the p-value of the test is not less than 0.05, we fail to reject the null hypothesis. Right? We all agree on that one? We fail to reject the null hypothesis. Let's come back, let's look at this code. Notice Wilcoxon 2-sample test, right? Wilcoxon 2-sample test, 22.40, 22.40. Excuse me. All right, let's keep looking. This means that we do not have sufficient evidence to say that the number of push-ups completed is different between the individuals that received caffeine and those that did not. Okay, now let's take a look at this box plot right over here. Notice how it gives you a box plot right away, and you want to go ahead and kind of perform a visual inspection, right? If you kind of look at our outliers here, or the folks at their pointy ends, they're about the same, right? And our Q1 and our Q3, they're close, they're about the same. They look very similar, right? Like they're not off the grid from each other. However, from the box plot, we can see the groups that received caffeine tend to have higher push-up values, but the results of the man Whitney U test, we know that the 2 Griffin groups were not statistically significant, right? So what we're saying is, we can definitely see that the drug group, the caffeine group here, tend to have a little bit higher, although, I mean, I don't know, it's tough for me to go and even say that, but it is a little bit higher. Look, the Q3 is higher, the outlier is higher, the median and the mean is a little bit higher, but in fact, you know, what does the p-value say, right? The p-value says 0.22 or 0.2240. That's not less than 5. That's way higher. Therefore, we fail to reject the null hypothesis and that there is no difference. Okay? Great. Okay, so now let's come back. Let's come back to our table right here. Let's say, hypothetically, we have a scenario. We have a pre-post scenario, and that's going to go ahead and lend us to say, well, we want to do a paired sample t-test. But then we do our assumptions testing, and guess what? One of the assumptions were violated, right? Variances are too high, or data is not normally distributed. So, what test do? We do Wilcoxon signed rank test, right? That's the test now that we are most particularly interested in doing. Okay, so let's come back. This is the same convention that we've been doing this whole semester, right? Let's go through a scenario. Suppose a researcher wants to know if the carnivore diet leads to changes in waist circumferences, right? So to test this, what they did was they measured everybody's waist circumference before they embarked on the carnivore diet, and then gave them, 6 weeks of the carnivore diet. You can only eat meat for 6 weeks. That sounds awful, I have to say. And then they measured their waist circumference again, and they wanted to go ahead and see if there's a change, right? Eating the same amount of calories, 2,000 calories, but now it's 2,000 calories of meat, okay? So let's go ahead and let's test this out. So the data set and the SAS code that we're going to be working with is called Wilcoxon.xlsx and Wilcoxon.SAS, right? Same thing as before. What is the null and alternative hypothesis? What is the p-value? Is there a difference? Is there a difference in waist circumference before and after the carnivore diet? Great. Okay, so let's head back to SAS. Same thing again. We are going to upload our Wilcoxon data file. We're going to upload our Wilcoxon SAS code. We're going to open up our Wilcoxon SAS code, and then here we are, right? We're going to run this through. So, same as before, we're going to name this data set work.wilcoxon. We're going to change the data set location, and then we're going to change the sheet name to patient, because that's what it's called, right? And if you are not sure, open up the Excel file and look in the lower left-hand corner. We're going to hit Running Man. And you will see now we have 3 columns, right? We have one column that identifies the patient by a number, 1 through 9. We have the first waist circumference, and then we have the second waist circumference, right? And if you just look on a superficial glance, you're saying, wow, this person had a really wide waist, a 50-inch waist, and now they have a 38-inch waist. And this person had a 39-inch waist, and now has an 18.6-inch waist, right? Wow, big changes right over here. Okay, so the Wilcoxon test has one step in it that's a little bit different and a little bit new to you all. I don't want you to fret. Don't be scared. It's pretty straightforward, and you have this code, so you're ready to go, right? But what we need to go ahead and do for the Wilcoxon test is to take waist 1 and minus it from waist 2. Right, so 50 minus 38, that's going to be like 12 or 11.4, right? Something like that. That's what we're going to be expecting. So what's the difference between 1 to 2? So here we have 17 and 19, so the expectation is going to be -2, right? The difference between this column and that column is going to be -2. And in order to do that, you simply, whoops, wrong code. You simply go and you use this statement right here from 10 to 14, and you say data. We're going to create a new data set. We're going to call it Wilcoxon 2. Remember, we had it Wilcoxon 1. Now it's Wilcoxon 2. We're going to use Wilcoxon. We're going to create a new column that is equal to waist 1 minus waist 2. And then we're going to hit Running Man. So now, and let me just go ahead and show you a little bit more just in case. If we go to Libraries, and then we go down to our work folder down here, I already have a Wilcoxon 2 because I created it already, but let me delete Wilcoxon 2. So when you go to Libraries, My Libraries, Work, you should see Manu and Wilcoxon, assuming you're doing this all at the same time, but you'll definitely see Wilcoxon, right? What's going to happen is, what we're saying is, hey, we're going to create Wilcoxon 2, And I want this one extra column here, and I want you to take the two differences. And so watch this, running man. And if you see in our data frame, we have this new column now called diff, right? And that's exactly this minus this gives you that, right? So 17 minus 19 gives you -2, okay? And if we come back here under libraries, my libraries, and then work, notice now we have our manu, Wilcoxon, and Wilcoxon 2. So moving forward, the next step, we're going to use the Wilcoxon 2 data frame. And okay, so in order to run the Wilcoxon test, we use the proc univariate data equals Wilcoxon 2, and what we want to run is our diff var, right? The difference between weights 1 and weights 2, which we created in the step before. So let's highlight, let's do running man, and here we are. We have even more statistics again, right? Where we are interested in, we are going to scroll down. Where are we? Oh, here we go. Test for locations, right? And then you'll see signed rank all the way at the bottom. That's what it is. Wilcoxon signed rank. And you'll see our p-value is equal to 0.0547. Yikes! That was close, right? So let's go ahead. Let's take a look here. Oop, actually, I don't want to even skip ahead. Let's come back. So you're just listening along and not clicking along to the slides. This is a good time. Pause, right? The p-value is equal to 0.0547. Do we accept or do we reject? Right? Pause, answer this question, think about this for a second, because we're really close. Okay, here we go. Recall that the Wilcoxon signed rank test uses the following null and alternative hypothesis. The waist circumference between the groups is equal between the two groups. The waist circumference is not equal. Since the p-value of the test is 0.0547, is not less than 0.05, very close, we failed to reject the null hypothesis, right? So remember the key here, we're going to pay attention to this bottom one here that says signed ranks, and then you follow the same convention. And folks, this is really it, right? This is the big difference. If the assumptions are violated, you do non-parametric tests. Simple as that. And then this is the grid. So next week, we are going to do the one-way ANOVA. We're going to, or the non-parametric version of the one-way ANOVA, the Kruskal-Wallis test right here. So I'd like you all to run through these exercises. Let's have a conversation about this. If we have any questions, let's reach out. And then I will see you all next week. Bye, everyone.